What is going on, everyone? So today we're going to be talking about op amps or operational amplifiers. I'm going to be explaining how they work, what they are, and how I, as an electrical engineer, might use one in the real world. Op amps are extremely versatile electronic components, and you can do a whole bunch of unique and cool things with them. So hopefully by the end of this video, you will be able to have enough information to be able to kind of start using them in your own circuits. Real quick, before we go any further though, please go ahead and drop a like on the video for me. It helps the channel out a ton, and subscribe if you'd like to stay up to date with any future videos. So a brief introduction. Op amps, or as you heard me say earlier, operational amplifiers, are a type of integrated circuit in the linear amplifiers category of components. So if you go on DigiKey's website and you navigate to the linear amplifiers category, you'll find a wide variety of different kinds of op amps that you can kind of choose from. Here, I mean, like there's 1,000 pages of op amps, so you have thousands of components. Just one example, though, is going to be this AD741JN op amp that is by Analog Devices. So this is just a typical general purpose op amp. So if you're interested in like learning more about some of the electrical parameters of them, just check out this product page here. I'll link it in the description below for you, actually. So the basic operation and anatomy of an op amp is as follows. The typical op amp has 5 pins that we ought to concern ourselves with. The first one is the non-inverting input. Then you have the inverting input, and you have the positive power supply, and then you have the negative power supply, and then finally you have the output. I actually drew these on a typical, so this little symbol right here is what you would see on a schematic if you saw an op amp present. So you would see these 5 pins. Sometimes you might see more, but for the purposes of this video, only worry about these 5 pins right here. A basic overview of how op amps work is typically you would have positive and or negative voltages applied to the input terminals, and that in turn will affect the output of the op amp. So a brief overview of how op amps work. So typically you would have positive and or negative voltages applied to these input terminals, and that in turn would affect the voltage of the output terminal. There are cases where you can have more than just input voltages connected to the input terminals. You can apply, you can connect other circuit elements such as like resistors, capacitors, things like that. And we'll talk about those later on in this video. But for the basics, just worry about understanding what I just explained. You have voltages on the input that affect the output. So the first example I want to talk about is one in which there's just voltages connected to the input, and then we're going to see how that affects the output. So in the first example I want to show you, it's going to be one where there's just voltages connected on the input, and then you have our supply rails, and then nothing is connected on the output. The first example I want to show you is one where you have nothing connected to the op amp besides 2 input voltages at each of the terminals. So the relationship between the input voltages at both of the terminals and the output voltage can be described as V out equals A times quantity V2 minus V1. In this case, V2 is we'll call it the positive input terminal or the non-inverting input terminal. And then V1 is the inverting input terminal, or we'll call it the negative input terminal. So the way you figure out what the output voltage is going to be is you take V out, you take V2 minus V1 and multiply it by A, and then A is referred to as the open loop gain in this case. So typical values of A, or open loop gains, of op amps in the real world range from about 10 to the 5th to 10 to the 8th. And then another important rule of operation for the op amp is that V out cannot exceed VCC. So I put the absolute value bars here, meaning just in both the positive and negative direction. So it can't go lower than that negative power supply, and it can't go higher than the positive power supply. That makes sense. So if V out is operating in, or if V out would otherwise be greater than or outside the bounds of these positive and negative power supplies, it is referred to as being in the saturation region. And then if V out is going to be within that range of the positive and negative power supply, it's referred to as operating in the linear region. So one thing you might have noticed already is that because A, aka the open loop gain, is so astronomically high, even the tiniest difference between V2 and V1 will cause the op amp to saturate. And this is exactly what happens in this case. So one thing I want to show is just this example I have right here. So you have 2 volts on the input and you have 2.1 volts on the output, right? And we're saturating at 5 volts really, because really what you would have is, if you did the math, you have 2.1 minus 2, And you would have, so that's 0.1 volts times like 10 to the fifth, which would be a lot higher than just 5 volts. So it's gonna saturate no matter what. So this is exactly what you'd expect. And we'll just change this value here like 2.2, and then we'll see it goes all the way to like the lowest value. One thing I guess I'll point out here too is a way that the most common ways you'll see op amps operating is that you'll have your positive supply, or I'll say you'll have, we'll refer to this as like one-sided operation, where you have one supply, be it positive or negative, and the other part is grounded, because very rarely will you have a signal that actually ranges from that goes from a negative to a positive, right? You'll always be operating either all negative to zero, or zero to positive, right? Hopefully that made sense, because otherwise you'd have to go through the trouble of acquiring a negative voltage source, and that's just a real pain to try to do in like modern electronics. So it's way easier just to find like a little 5 volt power supply and then just connect it to the rail, and then you're good to go. But yeah, the key takeaway here is that even the tiniest difference in these voltages results in complete saturation of the op amp. So you're probably wondering then, how is this even useful if this is basically just like a switch, saturating on and off, left and right? Like, it doesn't really seem like it's that useful. So one way that these might be commonly used in the real world is that you would have one of these voltages would be referred to as like a reference voltage. So you might be you might say your reference voltage is like 2.5 volts. And then the other one would be like your quote unquote input voltage, right? And so basically what this acts as is a way to measure a voltage value. And so you would be able to say like, okay, whenever the switch is high, we know that our value is, whenever this is outputting 5 volts, we know that the signal is greater than 2.2 volts. And so one specific example that you might see in modern electronics is actually with power supplies. So if you remember some of the power supply videos we've done here, if you show me when I show a block diagram of the inside, the feedback voltage is actually sent into a type of op amp. And so it's compared to a like 1.1 or something, 0.7 volt reference voltage. So that's exactly what it's doing there. And that signal, effectively, it's allowing it to monitor the output voltage, and that's sent into like a control algorithm. And so that's how, modern power supplies actually work, is using op amps in this fashion. So one problem with this circuit, however, is because the op amp's output is so sensitive to even the tiniest difference between V in and V out, it actually becomes extremely susceptible to noise. So things like a transient voltage spike could easily cause this op amp to like trigger, one way or the other. And so maybe imagine that this op amp signal is being used to like trigger a cascade of events, a sequence of events. And, it puts a lot of strain or stress on your circuit to be, toggling out a whole bunch if you have like a really noisy signal. And so there's actually been a solution to this problem, and that solution is known as hysteresis. So what hysteresis is, or what the definition of hysteresis is that it means that the output lags behind the input. Now, I don't really think that's a particularly useful example in this case, because it doesn't really tell us what's going on or what effectively we're doing by invoking or by creating some hysteresis in our circuit. So let's take a look at this example of hysteresis. So in this diagram, we have the same general purpose op amp that we had before, only this time we've connected some external components to different terminals of the op amp. In order to understand what's going on here, I just want you to recall in the previous example we just looked at, where basically we demonstrated that because the open loop gain is so astronomically high that minuscule differences between V1 and V2 will cause the op amp to saturate one way or the other. What this effectively means is that our output is going to either be 5 volts, which is like the positive power supply here, the saturation limit, this upper saturation limit, or it's going to be 0 volts, which is the lower saturation limit. So let's analyze the circuit in those two contexts. So on the right hand side right here, you'll see that I've rearranged the 3 resistors in an equivalent but more easily understandable configuration. In this configuration, you can clearly see that what is really going on here is that we have 2 different voltage dividers being formed. One between the 100K resistor and the other 100K resistor, and then the other one between this 576K resistor and this 100K resistor. When the output is 5 volts, the voltage at this node, or this node right here at the input terminal, becomes 2.7 volts. That means that in order to get it to transition from a 5 volt output to a 0 volt output, V1 would need to reach above 2.7 volts. The second diagram shows the same configuration of resistors, only this time the output is 0 volts. So again, we have a voltage divider being formed by the 100K and 100K, as well as the 576 and 100K. The only difference, though, is that this time, since the 576K is grounded or 0 volts on this side, this causes the voltage at this node, again, this same little input terminal node right here, to be 2.3 volts. This means to get the output to transition from 0 volts to 5 volts, V1 would have to be less than 2.3 volts. So if you're not completely following what we've done here, is we basically created a little bit of a buffer zone between our transition levels, meaning the op amp won't transition one way or the other until it's above 2.7 or below 2.3. Meaning that little area in between, like they're no longer like hitting against each other, right? The transition modes. So it's a lot less susceptible to noise and transient voltage spikes and stuff like that. You can actually finally control the size of this buffer by just changing your resistor values to be whatever you want them to be. So that's like another benefit of this method. And this will help prevent rapid transitions due to signal noise. Let's just go ahead and take a look at the simulation I have, just so kind of make it extremely clear. So this configuration is exactly the same as the one in the diagram I just drew. It's just the terminals are flipped in this simulation. So that's why this is kind of looks like this, but it's exactly the same as what I just showed you. So here we have our 5 volt reference signal, and then we have our 2.8 volt input signal. So you can see if we drop it down to like 2.4, nothing changes. It only changes whenever we get below 2.3. So let's just go 2.2. And then we have 5 volts, right? And then if we just start ramping it back up a little, let's just go like 2.6. Again, nothing changes, right? Still 5 volts. It doesn't transition until we get to over 2.7, right? So 2.8, then it will transition, right? And so hopefully you see the difference between this and the previous example we just looked at, where even like a 0.1 volt difference completely change the output, right? In this case, you need a lot larger one. You have to go from, above 2.7 to below 2.3. So you're looking at a 0.6 volt difference. And again, like I mentioned, you can, by choosing different resistor values, you can affect this. You can affect the size of this buffer as much as you want. So now that we've covered some of the basic examples and operating principles of the op amp, let's talk about some more advanced configurations that you might see in modern electronic circuits. So these more advanced configurations actually require us to use some of our circuit analysis techniques, namely the Kirchhoff's current law and the node voltage method, in order to establish a relationship between the input and output voltages. And then I also want to cover, there are a couple advanced operating characteristics of the op amp that you need to know about in order to properly analyze the circuits. So the first rule or operating characteristic is that current into both input terminals is 0. So this is like a characteristic, a quality of the op amp, is that it will not allow any current to be flowing into its input terminal. Okay, so that is like a property of the op amp itself. It's not like a rule that we're setting up ourselves. It's just how op amps work. Another rule or another way that op amps work is that the voltage across both input terminals is equal to 0. So that is V2 minus V1 equals 0. Again, this is a property of the op amp and not like a rule that we're making up ourselves. So the first example I want to take a look at is a configuration known as an inverting amplifier. This configuration is denoted by our input voltage in series with a resistor that's connected to the inverting input terminal of the op amp, as well as a feedback resistor that connects the output back to the inverting input. Then you also have the non-inverting input being connected directly to ground or 0 volts. So what we want to do is we want to figure out the relationship between the output voltage and the input voltage. The way we begin to analyze this circuit is by doing Kirchhoff's current law at this first node V1 right here. So Kirchhoff's current law will state that the we'll call it II, which is the input current, is equal to the current I1, which is this current right here, plus IF, which is that current up there. And if you remember, the first rule we just explained is that I1 has to equal 0 because no current is allowed to flow into the op-amp input terminals. So if I1 equals 0, that means that the input current is equal to this feedback current, or IF, up here. These two are equal. So using the node voltage method, that means that VI minus V1 over R1 equals V1 minus V out divided by RF. And then this is when we use our second rule, which is that this is when we recall our second rule of op amps, which is that the voltages at the two terminals has to be the same, meaning that since V2 is connected to 0 volts or ground, that means the voltage is 0 volts at this terminal. That means the voltage at V1 also has to be 0 volts. So whenever you set V1 equal to 0 volts, the expression simplifies down to VI over R1 equals negative V out over RF. So when you just do the algebra, this is what our gain equation comes out to be. So you just get negative RF over R1 times VI. This is the relationship between the output voltage and the input voltage. As you can see, this is called an inverting amplifier because the output voltage is equal to some negative value times the input voltage. So let's take a look at a circuit simulation so we can see some real numbers and kind of understand a little bit more about how this circuit works. So here we just have a 100K resistor and another 100K resistor, then we have a 2 volt input. So if you look according to the gain equation, that V out is supposed to equal RF over Ri times the input, and since these are equal, that's just equal to 1. So that means the input is just supposed to be the negative of the output. So let's just change this value around. Let's just say like 3 volts. It's negative 3 volts. Just say, 1 volt, negative 1 volt. So as you can see, based on the gain equation, the output is kind of what we'd expect it to be. All right, so let's take a look at another example. This configuration is probably one of the most common configurations you'll see in all of electrical engineering. It is called the non-inverting amplifier. So much like the inverting amplifier, we have our input resistor as well as our feedback resistor. The only difference is that now the input voltage is going into the positive input terminal of our op amp, and then over here where the previous input voltage was, we are now grounding it. So the way we begin to analyze this circuit is exactly the same as the last example. We first do KCL at V1. So we know that the input current, I'm calling this II, the input current, just for the sake of being consistent. So the input current is equal to I1 plus IF. And again, we recall rule 1 of the advanced operating principles of op amps, that I1 is equal to 0. That means I is equal to IF. So then we convert this to voltages and resistances using the node voltage method. We know this is 0 volts right here. So we have 0 volts minus VI. We then recall the second advanced operating characteristic of op amps, that is that the voltages at the two input terminals has to be exactly the same. So that means V2 equals V1 equals VI. So that means when we convert this using the node voltage method, we get 0 volts minus VI equals VI minus V out. And so then when we do the same algebra to simplify the equation, we get V out equals 1 plus RF over R1 times VI. So this is referred to as the non-inverting amplifier because V out is some positive multiple of VI. So let's just real quickly look at another simulation to look at some real values to make sure we have an understanding of how this is working. So here with this configuration, again, we use 200K resistors. So if you recall back to the gain equation, RF over R1 is equal to 1. So then you go 1 plus 1 equals 2. So that means V out should be twice that of V in. So we're going to double check that. So we get 1.5, we get 3. Let's just change it to 1. We get 2. Just change it to 2, 4, right? So on and so forth, right? So this operates, exactly as we'd expect it to. Now in this configuration, if we go back to our gain equation real quick, if you may have noticed that, let's say RF equals 0 or R1 equals infinity, this op amp, the gain of this op amp just becomes 1. And this is actually a special configuration of the non-inverting amplifier known as a voltage follower. So real quick, let's just go back to the simulation. So if we remove this resistor right here, see how it starts following it. So the output is exactly the same as the input. 1.5, 0.5, type 3.5, 4, right? So the output just follows the input directly. So one question you might have is, why would we ever use a circuit like this in the real world? Like, what are some actual applications of this? So there are two main reasons why you might actually use a voltage follower in the real world. The first one being that noise from the input signal does not transfer over to the output signal. That is because these are the input and the output are isolated whenever you use an op amp, so none of that noise can transfer over. The second reason might be that your input signal might not be able to supply enough current to whatever your output like receiver might be, right? So the way op amps work, I don't know if I made this clear, is that the supply current is actually coming from the positive and or negative power supply rails right here, V plus and V minus. So these things are the ones that are supplying the juice, so to speak. So you can have these hooked up to like, say, like a 5 volt 1 amp power supply, and you can be generating 1 amp of current on the output. Let's say like your input signal might be like a micro, GPIO of a microcontroller, which can only source like 16 milliamps or something, and say you need a lot more for some reason. Then, if you hook this up to an op amp, you can really get as much juice as you need out of this puppy by using, the positive power supply or the negative power supply. So those are a couple of reasons you might want to use a voltage follower. So there are a lot more configurations of op amps besides the ones we have covered today, but hopefully I've kind of given you the tools necessary to be able to analyze any op amp circuit that you want. Like the steps are going to be the same every single time that we followed. So just go back. If you have an op amp that you don't know how to analyze, just follow the same steps that we followed for the other ones we did today, and you should be able to solve it. That pretty much wraps up everything I wanted to cover in this video. Thank you so much if you made it to the end, and hopefully I will see you in the next one.